Welcome to the second video of our module on data-driven distribution system planning. My name is Pedro Vergara, and today we will discuss how distribution systems are planned. Distribution system planning refers to the definition of the future investments needed due to increasing consumption and local generation. A proper distribution system planning approach identifies the network bottlenecks in advance and plans for timely infrastructure upgrades. When planning, more than just the technical aspects are considered. For instance, safety, reliability, durability, flexibility, and transparency in decisions also need to be taken into account. Traditionally, distribution system planning relies on robust but conservative assumptions. Some design assumptions include approximations are used based on type of customers, household, offices, shops, and industry. Customers are modeled based on average profiles and maximum peak demand information. Let's see an example of a design of a low-voltage residential network. In this case, we will plan following a worst-case scenario. We will plan for peak demand to ensure reliability. We will also make use of this concept, simultaneity factor. Simultaneity factor is an estimate between 0 and 1 of how many users will demand full power simultaneously. Let's define the transformer capacity for a low-voltage network with 100 residential customers. Let's assume that each customer uses 4,500 kWh per year, and we assume a peak power of 2.6 kilowatts and a power factor of 0.90. Let's also assume a simultaneity factor of 0.46 for 100 houses. Finally, as a design criteria, let's assume that the demand increases 1% annually and that we are planning for the next 30 years and include a 10% safety margin. Using the expression that you see in the slide, we reach an estimation of 177 kilowatts for the transformer. To estimate the apparent power of the transformer, we use the expression in this slide to obtain 197 kilovolt ampere. A standardized value of such transformer would be of 250 kilovolt ampere. If we repeat the same design calculations now considering that all houses will include a 5 kilowatt heat pump, we will reach a new estimate for the transformer of 1000 kilovolt ampere. This is the moment to pause the video to check how these calculations were done. As you can see, we have obtained now a transformer that is 4 times larger in capacity than the previous design. The challenge is that if all Dutch neighborhoods would need to do the same transformer upgrade, the financial cost would be extremely large. Until now, we have learned that distribution system planning is done following a worst-case scenario, with a small probabilistic component. This approach has 3 major flaws. First, it is overly conservative. Assets are oversized for rare worst-case scenarios, increasing cost. Second, it does not include any risk estimation. Planning is done in a deterministic way, and it doesn't account for probabilities or uncertainties. Third, there is a loss of critical information. For instance, by only considering the peak demand value, the peak demand timing is ignored, which is important when flexibility is needed. And finally, user behavior. The average profile hides individual patterns, for example, which users can provide flexibility. Planning under such a conservative approach will have a societal impact. This impact is better understood via the energy trilemma, in which we must balance between sustainability, affordability, and reliability. The question is, can we invest our way out of congestion? The answer is no. While investment helps, we need smarter planning. Consider only the cost of a new medium voltage substation. The challenge here is the large number of such substations that might need to be built, besides the required space and time to realize them. Here is our hypothesis. If we incorporate risk and uncertainty into planning, we can reduce future investment costs while maintaining reliability. And this is where generative AI comes in. By modeling real-world variability, not just worst case, we can optimize grid designs for realistic scenarios. To summarize, future investments will ease congestion, but it will not solve the problem completely. We need data-driven methods to balance sustainability, affordability, and reliability. In our next video, we'll dive into how generative AI can transform distribution system planning.